Today we talk about capacitance of cylindrical capacitor. What we mean by capacitor? A capacitor is like a bag where we store the charges. Remember, we have positive and negative charges. For this bag has to be specific. It consists of two conducting objects, usually are plate or sheet. This plate or sheet are closed to each other, but they don't touch. If they touch the charge, they go back with each other and we get a neutralized plate. The objective of having a capacitor is to store the charges we can use later when we need it. In this example, we are going to calculate or find the formula for the capacitance of the cylindrical capacitor. A cylindrical capacitor consists of cylinder of radius R1 is the inner cylinder surrounded with shell. This cylindrical shell outside has radius R2. Both cylinders have the same length. We call it L. The inner cylinder is charged positively and the outer cylinder is charged negatively. Now this picture is the top view of this cylindrical capacitor. The inner cylinder is positively charged with radius R1 and the outer cylinder has radius R2 and is charged negatively. The objective is to find the capacitance of this cylindrical capacitor. We need to calculate the electric potential difference between R1 and R2. Once we find the electric potential difference between R1 and R2, and then we will find the capacitance. Now, let's calculate the electric potential difference between R1 and R2. The electric potential difference between R1 and R2, by definition, is given by V1 minus V2 to be the integral from R1, where V1 is, to R2 E dl. So we need to find the direction of E and dl. dl, it goes from R1 to R2. Now when we go from R1 to R2, we go radial, we go in that direction. The same thing for electric field. The electric field goes from positive charge to negative charge. The electric field between these two cylinders will be outward. It will be going from positive to negative. If I go here, it will be in that direction. If I go in that, it will be in that direction, etc. Okay? The electric field will be outward. The displacement also is outward. That means we said by definition E dl is E dl cosine of theta. Theta is the angle between the electric field direction and the displacement direction. Between E and dl, there is 0 degree. Cosine of 0, it will be just 1. This E dl. Now we say dl is radial. We just put dl is dr. Now electric potential V1 minus V2, we just integral from R1 to R2 E dr. Now, in order for us to find this electric potential, first we need to find this electric field between these cylinders. That means we need to go and find this electric field in this zone. To find the electric field in this zone, I will use Gauss's law. We said the definition of Gauss's law is the integral on a closed area E times dA. It will be just Q enclosed over epsilon 0. This Q enclosed is just the charge we have there, which is plus Q over epsilon 0. Now remember, this is our cylinder. This is just top view. The electric field will be outward. This flux, electric flux, we have three areas. This area, we call it the base. The other area will be the base. Remember, the dA and electric field, they are perpendicular on the base. The only area we have left is lateral area, where dA and the electric field are in the same direction. So all this flux we have here is produced by the lateral area. So in this case, electric flux, it will be just E integral of dA, which is Q over epsilon 0. Remember, I put E outside because all the way on the lateral area, it will be fixed, it will be constant in magnitude, and why there is no angle, because the electric field and the lateral area vector, they are in the same direction. This is why EDA cosine theta, the cosine theta is 1. Now let's find this lateral area. The lateral area will be the length times the circumference of this cylinder. The circumference is 2 pi r. We said the Gaussian cylinder, we call it just the radius of Gaussian cylinder is just r. So this area, the integral of this area, will be just 2 pi r, which is the circumference times the lateral area. And this is Q over epsilon 0. We said the electric field will be just Q over 2 pi epsilon 0 times the length times r. This is the electric field in between these two cylinders. Now, once we find the electric field, using Gauss's law, set electric potential V1 minus V2, it will be just the integral E dr, and between R1 and R2, and we found the electric field using Gauss's law, which is Q over 2 pi epsilon 0 r times the length of the cylinder, and dr. This is what will be the difference of electric potential between the 2 points 1 and 2. Point 1 is what is the radius 1, and point 2 what is the radius 2. So this term Q over 2 pi epsilon 0 and L are constant. We can take them outside the integral. What we will have? Q over 2 pi epsilon 0 L integral of dr over r between r1 and r2. This integral of dr over r is just natural logarithm, and the natural logarithm will be between r1 and r2. So this v1 minus v2 will be just q over 2 pi epsilon 0 L factor of natural logarithm of r2 minus natural logarithm of r1. So we can put this, it will be just ln, this term is just ln of r2 over r1. Now the electric potential will be, now all we need to do is to identify the capacitance from this formula. So we know V1 minus V2 equals Q over C. So what will be C? V1 minus V2 times C equals to Q. So if I move this term to the other side, what will be? It will be what? V1 minus V2 times 2 pi epsilon 0 L over the natural logarithm of R2 over R1. So if I identify this, C will be this. So the capacitance of this cylindrical capacitor will be just 2 pi epsilon 0 L over natural logarithm of R2 over R1. The capacitance will be 2 pi epsilon 0 L over ln of R2 over R1.